This lecture finishes up Chapter 5 for us, and it goes over a theory of bonding called the valence bond theory. So far, all we've talked about is the Lewis electron dot theory of bonding, which is very handy. It allows us to see the valence electrons of all atoms involved in making bonds and how the valence electrons shift and the resultant molecular shapes and bond angles. However, where Lewis dot theory falls short is accounting for the orbitals. Now, we know valence electrons exist in orbitals, a region of space, but no matter how we finagle the atomic orbitals that we're familiar with, s, p, d, and f, we cannot come up with the shapes that we know molecules have. So it was time for a different theory. The next theory to come along was a theory of hybridization, which focused on the orbitals of atoms that are forming a bond. It was developed by a scientist named Linus Pauling, and basically, oversimplistically, he said that the atomic orbitals that atoms have that are forming a bond kind of blend together when they are making a bond to form what we call a hybrid orbital. Okay, it's a combination of those atomic orbitals. This hybridization gets mildly complex, so you probably have to really kind of focus and make sure you understand what I'm getting ready to say. For example, if an s atomic orbital combines with 3 p atomic orbitals, okay, so what do we have so far? We have an s and we have 3 p atomic orbitals, right? If they blend together to make a hybrid orbital, we designate that hybrid orbital as an sp3 hybrid orbital, okay? So hopefully you can see how it got its name, right? The hybrid orbitals are named after how many of the atomic orbitals were used to make them. Now, there's something important that you need to keep in mind, and we call it conservation of orbitals. So however many atomic orbitals you start with, in this case 4, you must end up with the same number of hybrid orbitals. So merging an s and 3 atomic orbitals will give you 4 equivalent sp3 hybrid orbitals. So why do we do that? Probably the easiest way to show the advantage of the hybridization theory is to show the explanation it gives for carbon. So the electron configuration for carbon, the ending of it anyway, is here. And so carbon, we know, has 4 valence electrons, right? It's in group 4a. But if you were just to glance at the orbital configuration for carbon and just think of the Lewis electron dot theory, it might look at first glance that carbon really only wants to make 2 bonds, right? It has 2 unpaired electrons, but we know that carbon makes 4 bonds. So how does the valence bond theory or hybridization theory account for the 4 bonds that carbon makes? What the hybridization theory says is that one of the electrons from the s atomic orbital gets promoted to one of the empty p orbitals. And so what you have then, obviously, would be an intermediate before they blended, before they hybridized, that look like this, right? All right, and then because we know all 4 bonds of carbon are equivalent, okay, there isn't like one that might be made of an s atomic orbital that would be a little bit different than the 3 bonds made from a p. That's where hybridization comes in. So the hybridization theory says that these 4 atomic orbitals blend together to make 4 equivalent sp3 hybrids. And that now explains why carbon makes 4 equivalent bonds, each with an identical orbital. And it also accounts for the shape and bond angles of a carbon atom that has 4 bonds, okay? In other words, a tetrahedral shape, okay? We have 4 equivalent electron domains. Again, they're equivalent, so they're equally spaced from each other in space, which we know to be true. So that part of the valence bond theory has worked great. Let's talk about the different types of hybrid orbitals now. We talked about sp3, and that would be for a molecule that has 4 electron domains about a central atom. Okay, and that would be associated with a tetrahedral electron domain shape. All right, so examples would be methane, carbon tetrahydride, or ammonia, right? We know that nitrogen has a lone pair in ammonia, so it has 4 electron domains. So these would be 2 examples that exhibit sp3 hybridization and tetrahedral geometry. Let's look now at sp2 hybridization. So hopefully you understand the naming or the symbol we use for hybrid orbitals now. That suggests to us that the sp2 hybrids are made from 1 s atomic orbital and 2 p atomic orbitals, okay? So here's the 1s, here are 2 of the p's, okay? Now keep in mind, tuck in the back of your head, that we know in every p sublevel there are 3 p orbitals, okay? So there's a leftover p orbital not being used with sp2 hybrids, okay? So just kind of tuck that in the back of your mind. So now when these 3 atomic orbitals combine or blend, hybridize, they form 3 equivalent. We started with 3 atomic, so we're going to get 3 molecular equivalent hybrid orbitals. And you can predict what shape that's associated with, right? 3 domains, 1 for each orbital, which is trigonal planar, right? And so sp2 is associated with trigonal planar shape and 120-degree bond angles. Now, the leftover p orbital, atomic p orbital that is not used for one of the electron domains, you'll see as we go along, remains unhybridized. It remains as an atomic p orbital, and it's used for what we call pi bonds. So if you remember, pi bonds are present in double and triple bonds. Okay, so just as a quick reminder, a double bond has 1 sigma bond. Oh, that's a bad there. 1 sigma bond and 1 pi bond. And a triple bond has 1 sigma bond and 2 pi bonds. All right, so the theory is that the non-hybridized atomic p orbitals that are left over are used to make these pi bonds. Let's look at an example of a compound that has sp2 hybridization and a double bond. So this happens to be formaldehyde. Okay, CH2O would be the formula. And we can see it has 3 domains, 1, 2, 3. So thinking of hybridization, when things have 3 domains, what is the type of hybridization? Well, hopefully you're starting to kind of catch on to that. If we have 3 domains, we need sp2 hybridization, right? Because that shows we started with 3 atomic orbitals, 1s and 2p. So that's 3 orbitals, right? So we're going to end up with 3 hybrid sp2 orbitals too, 1 for each domain. And again, the sp2 is associated with trigonal shape, of course, since it has 3 domains, trigonal planar. All right, so what I really want you to see here, though, is the use of the unhybridized leftover p orbital. So if we were to draw a picture, we would draw that the carbon had 3 sp2 hybrid orbitals that were used to form the single bonds. So one single bond was to hydrogen. Actually, two of them were to hydrogen, right? And then we had one sigma bond to oxygen. Okay, we need another bond to oxygen, the double bond. And so the theory is that, let's look at the individual atoms that are making the bond, carbon and oxygen. Okay, so again, each of these hybridize to make sp2 hybrid orbitals, okay, because each of them are going to have 3 domains when they're done. So these sp2 orbitals, hybrid orbitals, one on each atom, are going to come together to make the alpha bond between carbon and oxygen. Now, we know that carbon and oxygen have a double bond, okay? So the theory is that the unhybridized p orbital on each of them, because they're each sp2 hybridized, is used to make the pi bond, okay? And so that explains the double bonding. This is a complex picture, and you may have to revisit a couple times to truly understand the orbitals that are shown there, but it's a real useful, valuable diagram also. So the next hybrid we can get is sp hybridization, and as its name suggests, it is made from one s orbital and one p orbital, okay? And so since we started with 2 atomic orbitals, we get 2 hybrid orbitals, conservation of orbitals, okay? And makes total sense when you combine those hybrid orbitals. So if you have a central atom with 2 domains, okay, these orbitals account for the linear shape and the bond angle of 180 degrees. So this hybrid theory is working pretty well as far as shapes and angles go. Now, keep in mind we've only used one of the available 3 p orbitals, okay? Again, a p sublevel always has 3 orbitals. We've only used one of them. So there are 2 unhybridized p orbitals left over in sp hybridization. So that means that atoms that form sp hybrid orbitals also must want to make multiple bonds. They want to make 2 multiple bonds because they have 2 leftover unhybridized p orbitals. So let's look at some examples of compounds that are sp hybridized. Keep in mind that anything that's sp hybridized has 2 multiple bonds, 2 pi bonds. So you could have 2 pi bonds in a couple different ways. You could have 2 double bonds, each double bond having a pi bond in it, or you could have 1 triple bond, because remember, a triple bond has 2 pi bonds in it. So either one of these situations would give you sp hybridization. Let's look at an example of a compound that has sp hybridization. So we can see that the carbon here, go back to think about domains in Lewis dot structure, it has 1, 2 domains, right? So what you would do, let's say you were trying to identify the hybridization, you would first count how many domains, and then you'd say, okay, 2 domains. I need a hybrid orbital for each domain. In other words, I need 2 hybrid orbitals, 1 for each domain. So 2 hybrid orbitals would be sp hybrids. I'm going to end up with 2 sp hybrids. Okay, and that accounts for the sigma bonds. Now, all single bonds are sigma bonds, all right? Now, we have to account for 2 pi bonds now. And luckily, with sp hybridization, we have 2 leftover unhybridized p orbitals. And that's what's used to make the multiple bonds, or the pi bonds, okay? So let's summarize what we have so far. Remember that steric number is just another term for electron domains. So if we have only 2 electron domains, our hybridization is going to be sp, just as we said. That's associated with a linear shape, 180 degree bond angle. If we have 3 electron domains, it is we need 3 hybrid orbitals, so that means sp2. Now keep in mind that sp hybridization gives you 2 sp orbitals. Hybridization gives you 3 sp2 orbitals. Hybridization gives you 4 sp3. Remember, you end up with the same number of hybrid orbitals that you started with atomic orbitals. All right, so the only new thing here, you should already know the correlation between the number of domains and the shape and angles. What's new here is the hybridization associated with that number of domains and shape. So make sure that you know where each of these hybridizations fit into the knowledge about shapes. Okay, couple words about sigma and pi bonds, which I introduced a couple slides ago. What is the difference between a sigma and a pi bond? Well, the definition is that a sigma bond results from head-to-head overlap, okay? Direct head-to-head overlap of orbitals. That is a sigma bond. Sigma bonds are stronger than pi bonds. And hybrid orbitals always create the sigma bonds. All right, pi bonds made from unhybridized p orbitals. Those bonds are, well, all bonds are overlap from orbitals. You have to overlap the region of space where the bonding electrons are likely to be found, which means you have to overlap the orbitals. So a pi bond results from overlap, shoulder-to-shoulder overlap. Think of it that way, sideways overlap. It's not as strong of an overlap, and so pi bonds are weaker, okay, from the side-to-side overlap. And again, a reminder, all single bonds are sigma. Double bonds contain 1 sigma and 1 pi, and triple bonds contain 1 sigma and 2 pi bonds. Now, one of the things you should be able to do, and it's a real common multiple choice question on exams, is be able to look at a more complex structure and identify the number of sigma and pi bonds. So what if I made this a little bit trickier than it is here and gave you the structure that looked like this, okay? You would have to realize that CH3 means what I'm drawing right now, means a carbon with 3 hydrogens drawn on it. Then you would have to know again enough about Lewis dot structures that you would determine there is a triple bond between carbon and nitrogen. So now counting the total number of sigma and pi bonds, again, every single bond is a sigma bond, 1, 2, 3, 4. And then in a triple bond, one of the 3 bonds is sigma, so that makes 5. So there are 5 sigma bonds, and then counting pi bonds, there are 2 pi bonds. Every triple bond has 2 pi bonds. All right, and if the question happened to ask for a non-bonding pair of electrons, lone pairs, there is 1 on the nitrogen. So look forward to this type of question as multiple choice on your next exam. So summarize, again, it's always better to understand where correlations come from, but I realize the value of summarizing and quick memorization too. So you should be able to look at a chemical formula and identify the hybridizations of all of the atoms involved. So if the atom involved has only single bonds, such as this compound, this happens to be ethane. Okay, so if the atoms involved have only single bonds, it is sp3 hybridization. If an atom has one multiple bond, like a double bond, I shouldn't say any multiple bond, double bond, it is sp2 hybridization because it needs that p atomic orbital to make a double bond. If an atom is involved in a triple bond, its hybridization must be sp, okay, just like this other carbon would be sp also. So look now that every atom that involves a triple bond is sp hybridized. Every atom that is involved in a double bond is sp2 hybridized, okay? And then, of course, every atom that has only single bonds is sp3. Now we're going to review the larger number of electron domains. 5 electron domains, which we know is trigonal bipyramidal, right? And 6 domains, which we know as octahedral geometry. So once we have sp3 hybridization, we've used up all the s and p atomic orbitals. So s sublevel has 1 orbital, p sublevel has 3. What do we do when we've used those up? But we still need more domains. Those are for the atoms that expand their octet. That's when we go to the d sublevel, which we know has 5 orbitals in it. And so 5 electron domains are going to be sp3d. Okay, remember you need the same number of atomic orbitals as you need molecular bonding orbitals. So 1s, 3p, and 1d. Okay, 1 plus 3 plus 1. Okay, so it started with 5 atomic orbitals. That means it will give us 5 hybrid molecular bonding orbitals. Now, just to note that for 5 electron domains, we've used only 1 of the available d orbitals. Okay, there are 4 leftover d orbitals that are unused with 5 electron domains. Just heads up, empty d orbitals can be used to make pi bonds just like empty p orbitals can. 6 electron domains. Okay, so that means we need 6 hybrid orbitals. Remember, 1 for each domain. If we need 6 hybrid orbitals, it means we need to start with 6 atomic orbitals. So that's an s, 3p, and now we need 2d. Okay, so we need to start with 6 atomic orbitals. And that gives us, when you combine them, sp3d2. So here's a handy table summarizing the different hybridization and the shapes they're associated with. So this is something you should absolutely be able to recall quickly. So now when you work on practice problems that start with Lewis dot structures, then go on to shape, molecular shape, electron domain shape, and polarity, you now need to include in all of that hybridization, all right, of each atom involved in it, particularly the central, but each atom. Here are the general steps you'll be going through with the hybridization problem, and as with everything we've done in the last couple of chapters, start out by drawing the Lewis dot structure, because you won't be able to know how many domains you have until you do that. Count the electron domains around the central atom. Use the Vesper theory to predict electron group geometry and molecular geometry, okay? And then select the hybridization that goes along with the electron group geometry. So keep in mind that every single domain needs a hybrid orbital. And that is it for hybridization. There is a molecular bonding theory that is more widely accepted now than the hybridization valence bond theory, and that is molecular orbital theory. So you'll be introduced to that if you take organic chemistry.